As we've said, for a spherical reflector, the focus occurs for all the rays that come in parallel. It occurs along the central ray, the ray which comes back along the incoming path, and the focus occurs for small distances from the center ray, which is equivalent to saying for small incident angles. Okay, if we got a ray that's close to the central ray, then the tangent line will be almost horizontal. The normal will be almost parallel to the central ray. We'll have a very small angle of incidence, so we'll have a very small angle of refraction, of reflection in this case. Now, that focus for a spherical reflector occurs at half the radius. So if we have a spherical reflector of radius r, the reflection takes place at radius 1/2, or a distance 1/2 r from that mirror. Now we analyze a sphere full of water. Okay? We can actually look at a sphere full of water. Excuse me, I didn't have the sphere as close as I thought I did. Let's look at what happens. Okay, right here is a Christmas tree ornament full of water. I can shine the laser through the ornament. So I'm going to bring the laser over to this side. Notice how the image of the laser gets magnified. Matter of fact, I didn't realize you'd be able to see this quite as clearly as you can, but let's look at what happens. As I move the magnifier away, it gets bigger and bigger until it suddenly just kind of blurs out of existence at about this point, and then it comes back and we see it again. If I do the same thing, let's put the thing upside down so we can see that exactly what's happening. So we have a magnifier here. This thing gets magnified, bigger and bigger. At this point, it reaches its maximum size, kind of blurs out of existence right around here, and then comes back, and we can see it again. We can notice that here it appears right side up. That is, well, it's upside down, but it appears upside down just as it is. So the image is just the same, in the same orientation as the object, pointing downward. If I move back to here, we see that the image is now upward. So the image is inverted from its actual orientation. Okay, so you kind of see that. Now, the other thing I wanted you to see, I'm going to shine a laser in your eyes here. Well, let's see, it might not be such a good idea. That's kind of... Okay, I'm moving back and forth here. And I'm moving the whole distance. Let's see, let's get... See, I'm moving all the way out to here. You see the spot that I get when I'm all the way at the edge, and then I come back to the middle, and of course everything converges. Then I come back to the edge here, and there's the spot. So the spot only moves from about here to here as I move the laser the whole distance from one radius, or from one edge to the other. And that's kind of interesting, and we want to see why that happens, and we want to explore the mathematics of exactly what happens there. Now let's see, I'm trying to set this thing down in such a way that it won't roll over and spill all over everything. Okay, so we have a sphere full of water. The water has an index refraction about 1.33. I think maybe it's closer to 1.34. But this depicts the sphere with a center right here. Now, a central ray comes in, and as you saw, the central ray comes through and meets itself undeflected all the way through and out the other side of the sphere. A ray at distance delta x from the central ray will come in and be deflected toward the center. Now the question is, will that ray cross the central ray while it's still within the sphere, or will it be somewhere on the other side of the sphere? Looking a little more closely, at the factors that we have here, radius r, distance delta x, we have an angle theta sub I, that's the angle of incidence. The normal line is just a radial line, that's a line extending from the center on out. And it's of course perpendicular to the surface of the mirror at that point, tangent.